Hello students, today we are going to see what are the thermodynamic potential. So before going to see what is thermodynamic potential, we will see some mathematical steps. According to first law, we know from the first law of thermodynamics, we can write dq is equal to du plus dw. We all know that. So in case of exact differentials, we can write this as T ds is equal to du, because du itself is a exact derivative, plus P dv. Now from this, if I have to write the value of du, it will become du is equal to T ds minus P dv. Okay, so let's call this equation as equation number 1. Now from this, what we can see, at constant T and P, if volume is changing and entropy is also changing because of the change in volume, we get the change in internal energy du. So if we are controlling the volume only and we are keeping T and P constant, in that case only this equation is very useful. Okay, because it is just function of S and P. It changes as S and V is changing. But in cases where we are not changing S and V, that is not very useful. Okay, if we are changing pressure, then this equation is not very useful, and therefore we have 3 more equations like this, which we will call as functions or thermodynamic potentials, which can give relations between other 2 variables also. So basically, which variables we do have? We have P, V, T and S. Okay, these 4 are different variables we are using in thermodynamics. So this is basically in the hydrostatic system. In some other system there may be more variables, but we are just looking for hydrostatic variables. So these are 4 variables. Now in this equation number 1, we can only change V and S. We cannot change P and T. So what if there are other variables which are changing other than S and V? Therefore let's define one more function which is called as enthalpy. This enthalpy is generally denoted by letter H. You might have seen this in your chemistry classes. We use enthalpy. Here H is equivalent to U plus PV, where P and V are the variables and U is the thermodynamic potential, which we have seen earlier. du was a thermodynamic potential. So when we differentiate this, we will get dH is equal to du plus P dv plus V dp. Now using the equation number 1, we know du is T ds minus P dv. So substituting that, we will get T ds minus P dv plus P dv plus V dp. So here you can see minus P dv plus P dv will get cancelled out, and we will get dH is equal to T ds plus V dp. Okay, let's call this as equation number 2. Now here you can see, here the pressure is variable. We can control the pressure, and V and T is constant. So in that cases, this potential will be useful to us or convenient in case of, let's say, the problems which involve the heat quantities like heat capacity or latent heat, like that, or heats of reaction. You might have seen heat enthalpy we use in chemistry classes. So basically these are the quantities where we use this equation. Again, we will define one more term, one more function, which is denoted by A and which is equivalent to U minus Ts. So this function sometimes is also denoted by F. In some books you will see this as F. This function is called Helmholtz function. or Helmholtz energy. Okay, again differentiating this, we will get dA is equal to du minus Tds minus S dt. Substituting du from equation number 1, we will get Tds minus Pdv minus Tds minus S dt. So here Tds will get cancelled and we will get dA is equal to minus Pdv minus S dt. So let's call this as equation number 3. So in case of Helmholtz energy or Helmholtz function, we can change the volume as well as temperature, and this is most convenient variables we use in case of thermodynamics or statistical mechanics. When we use partition functions, this variable or this Helmholtz energy is very useful to use. Let's define one more function g, which is equal to or equivalent to h minus ts, where h is enthalpy we have seen earlier, and using that we will define this function which is called Gibbs energy or Gibbs function. Now again we have to differentiate this as we have done earlier. dg is equal to dh minus tds minus s dt. Now let's see what is dh from the earlier equation number 2. It is tds plus vdp, tds plus vdp minus tds minus s dt. Now here also tds is getting cancelled, vdp minus s dt. So this is nothing but dg. So in case of phase transition, okay, different type of phase transitions are there. So in those cases where we control pressure and temperature, or we can measure the changes in pressure and temperature, we can use this kind of functions. In some chemical reactions also we use this thermodynamic potential. Okay, let's call this as equation number 4. Now I will write these functions again. We know there is u, then we have defined h as u plus pv, then we have defined Helmholtz function which is u minus ts, and then at the end there was Gibbs energy which was defined as h minus ts. So these are thermodynamic functions or thermodynamic energies. These have the dimension of energy. And why we use this? We can use this any of 4 as a fundamental set of functions, because it has advantage that all have energy units and therefore they are conserved in certain cases. In some cases du might be conserved, like for example in isothermal processes u will be conserved, so we will use equation number 1 in that case, and it will be easier to find out the values of thermodynamic variables also. So I will show you later. We have the enthalpy. We got the enthalpy using the internal energy and product of 2 thermodynamic variable. Again we get a as a function of u, which is derived from the other thermodynamic variable and product of 2 thermodynamic variables. Again Gibbs energy is also derived from the other thermodynamic potential and the product of 2 thermodynamic variables. These transformations are called Legendre transformation. So we will again rewrite the 4 equations which we have defined as thermodynamic potentials. Why I am writing this? Because we need to remember these functions, these equations. So if they are in front of you, all equations all together, then we may have some trick to remember these formulas. Now these are 4 equations we have seen earlier. du is minus pdv plus tds, dh is vdp plus tds, dA is minus pdv minus s dt, and dg is vdp minus s dt. So if you remember the sequence u h a g, then you can see there is pattern. There is minus PdV plus VdP, minus PdV plus VdP alternatively. And for the first two there is plus TdS, and for the next two there is minus SdT. So you can see the pattern and you may remember this. From this you can also see U is a function of V and S. So if V and S changing, U is changing, du is changing. H is a function of P and S. A is function of V and T, and G is a function of P and T. So I will show you from the equation number 1 how we can find out the pressure and temperature, and subsequently using following equations like dH, dA and dG, we can also find out V and S in different notations. So from the equation number 1, du is equal to minus PdV plus TdS. Let's say we have defined U is function of V and S, therefore du can be written as dA by U by dA by V at constant entropy into dV plus dou U by dou S at constant V into ds. So if we compare these two equations, let's say this is equation number 1 and this is equation number 5, because there are 4 other equations also there. So if we compare this, we can find out du by dV at constant S is equal to minus P. So you can find out the pressure from this equation, from this differential equation. Similarly, we get temperature from du by ds at constant volume by comparing equation number 5 and 1. Here I have compared the coefficients of dV and dV. Here we have compared coefficients of ds and ds, and from this we get this equation. And similarly from the other thermodynamic potentials we can get other thermodynamic variables also. The U internal energy as a function of V and S, and we can get P and T. Okay. Similarly, if we use the function of P and S, which is enthalpy, we can get other two variables like V and T. We can get V and T from here. We got P and T from here. The same process is there. If we use Helmholtz free energy, which is A, and it is function of V and T, then we can get variables P and S as a differential form. And from Gibbs energy, which is function of P and T, we can get V and S. So for certain process or for certain problem, first of all we have to define certain base energy or base function. Okay, any one of these four can be the base function. So from these equations we can find out, okay, one or two maybe. So for example, if I know internal energy function and Gibbs energy function, then I can find out all the functions P, T, V, S, right? But it depends on the problem, which problem is given to you, and accordingly we can find out the other quantities.